So we're at the point where we're ready to start including friction in our calculations with forces. Calculating friction is not difficult, but you're going to find these questions require more steps for you to follow. So you're going to have to get used to drawing a diagram. It's going to be really important, and just thinking about how the information goes together. So I'm going to do about 5 examples with you. And then there's a sheet of practice questions. If you want to have a video lesson posted for the practice questions, I'm more than willing to. Otherwise, the answers are at the bottom of the page. And that will let you go through, and then there's a short quiz on Sam. So first of all, what is friction? So friction, I mean, we're really familiar with friction. That's not a new concept for us. But friction's a contact force. So it requires contact with a surface. That's what we mean by contact force, whenever two surfaces move past each other. So it's caused by the irregularities or the roughness in the two surfaces that cause them to catch. That is something that is a concern in most trades, because friction with surface roughness, something rubbing together, results in heat. Whenever we have heat result, that means some of the mechanical energy is actually being converted into heat energy, so we're going to lose efficiency. Not only that, but if the temperatures reach the right temperature, it can cause deformation of metals or materials or structural issues, which results in problems for us and can result in mechanical failure. So friction is something that's important to consider. And maybe you don't necessarily calculate it, I realize that, but understanding how it works and things that will reduce friction, because if we can reduce friction, we should be able to make work easier for us most of the time. Now, one important thing to take note of is friction is always opposite the motion of an object. Okay, so it's never going to be in the same direction as motion. It will always oppose motion. So for that reason, you're going to want to diagram your scenario, and you're going to want to probably label the direction the object is moving or the direction you would expect it to move. You'll understand why I'm saying expecting it to move, to determine where to put your force of friction arrow or your vector. So how to calculate the force of friction? The force of friction is a very easy calculation. You'll notice most of our calculations, like force equals mass times acceleration, we're getting away from those complicated kinematics equations. So the equations are getting more simple, but kind of the background work or the background thinking might be slightly more complex. So the force of friction is equal to mu. Mu is the coefficient of friction. Okay, my husband was looking at this the other day, and he says, force of friction is micro, what's Fn? And he's used to working in a trade where they use micro units, so they're looking at very small quantities of matter in water, because he's dealing with wastewater treatment. But when we just look at the letter itself, the letter is called mu, like a cat. And it's the coefficient of friction. It has no units. It's just a number that basically tells us what percentage of the normal force, what percentage of the force that the surface is putting on the object is converted to frictional force. So it's really kind of like a ratio. Normal force is the force that's perpendicular to the surface. So it's whatever force upwards the surface is putting on the object. Now we're going to have one scenario where normal force isn't necessarily upwards, and we'll look at one example of that. So knowing what the terms are is going to be really important. So you have normal force, and one of the key things to note is normal force is perpendicular to the surface. So which way will normal force be? If this is my surface, normal force, oh dear, that's definitely not perpendicular. Let's just erase all that. I'm going to see if I can try again. So my tablet has little dots on it, but they're not in the right places. Now this one will do. That's mostly straight. And if I go straight up, okay, they're right angles. So if this is a surface, this is my normal force, okay? It will always be in 90 degrees to the surface. We're going to get some examples that will be more like this one. And in that case, our normal force would be still right to the surface, So if this is my surface, there's my normal force. You know what's going to happen if we give you a vertical surface. The normal force is going to be straight out from the vertical surface. Okay, so normal force is always perpendicular. That's one of the key things to take note of. Now, I want you to think about friction for a second. There's two types of friction. We're not going to really focus on the types of friction so much other than just their qualitative properties, but I would expect you to know static or kinetic, those terms. So static friction is the friction of a stationary object. So let's say you have bearings in a race, okay? And there's no movement in that part, but there is going to be static friction that will have to be overcome in order to start movement. Once it starts moving, you have some kinetic friction there. Of course, you use lubricants in order to reduce that friction. It makes it more smooth between the surfaces. So static friction is before something moves. Kinetic friction is once something has started moving. Static friction is always greater than kinetic friction. That's just one of the rules. Okay, so I want you to think and apply for a second. In your experience, which requires less pushing force? So imagine you're pushing a crate or you're pushing a car. Maybe car is a good example. Does it take to get the object to start moving or to keep it moving? Now, I know a few times we've had one of the things is once an object is moving, it wants to keep moving. So momentum helps us a little bit, but that should help us remember that static friction is greater. It always creates, you'll notice there's be something heavy, and maybe this is me being slightly wussy. If there's something heavy I'm trying to move across the floor, you know how you do that kind of lean back and give it a good lean into, and then once it's moving, you can keep pushing it? That's because that static friction is greater than the kinetic friction, so it requires that little bit of extra force. Next time you go to move something heavy, think about that. Even if it's getting a bolt to move. I mean, corrosion results in increased friction. So let's say you have a bolt that you're trying to get loose. Once it starts to move, there's less friction involved. It's easier to turn. But sometimes to get that initial turn is a bit of a challenge. So you can think about the same scenario, because with a bolt in the nut, you've got two surfaces in contact, resulting in friction. Okay? And we know corrosion, if you have corrosion in between, you get even more roughness between the two surfaces, and that's what causes it to be even more difficult to turn. So there's lots of, we can think of all kinds of everyday examples in the work world where you encounter friction and you think about, and you might not think about it as being friction, but you do different things in order to minimize it. So let's get into some math questions now. I know it's your favorite part. I try to do some of those think and apply questions that aren't necessarily math, because I think that's maybe more how we use this in the trades. But we do have to do some of the math components as well. So our first example says we have a 3.75 kg block pushed along a tabletop with a force of 45 newtons. The coefficient of friction is 0.65. That means 65% of the force between the table and the block is going to be converted into frictional force. Okay, I really never thought of it being that way until maybe it was last year, just in the last couple years. I went, oh, that's exactly like doing a ratio. It's a ratio of the force of friction and the force between the surface and the object. One of those eureka moments, but it kind of helps to put that into perspective for us. I want you to find the force of friction, and I want you to find the acceleration of the object. So this question is going to take us a little bit to solve. So the first thing we always start with is a free body diagram. And my diagram is probably not going to look very pretty because it's just one of those days. So here's our block on our tabletop. Free body diagram says we need to label everything. So I often will put my block mass in the middle. So 3.75 kg. It's kind of like listing the knowns without making a list elsewhere. Force applied, well, we know it's being pushed across, so force applied is 45 newtons. Okay. Coefficient of friction, well, we know friction's going to be, if it's being pushed along the tabletop in this direction, force of friction needs to be in the opposite direction. There's our force of friction. And I'm just going to put next to it mu equals 0.65, just so that I have that information labeled with it. Now, downwards, we have the force of gravity. And then upwards, we have our normal force. Okay? Now that we have those pieces in place, we should stop and calculate any values that we know. So before we jump in and try to find what's the force of friction, go through and label your diagram. It might mean you end up calculating something you don't need later, and that's perfectly fine. But that means you also have all of the information, especially if you're one of these ones that maybe struggles a little bit with it. To label everything right at the beginning can be helpful. So the force of gravity is the weight of the object. It's not equal to kgs, it's newtons. So the force of gravity is going to be equal to mass times gravity, which is equal to 3.75 kgs times 9.81 equals 36.8 newtons. You'll notice the force of gravity is in newtons, whereas mass is in kilograms. I know we use those words incorrectly in our everyday life, and I'm not suggesting you go around saying my mass is 95 kgs. People are going to look at you and go, what the heck are you talking about? Just say weight. But we do use them incorrectly. So because of that, sometimes it causes a little confusion in a physics class. All right. Now this book, is it accelerating upwards or downwards? Well, it's being pushed along a surface. If it's being pushed on a surface, it's not going through the surface. It's not levitating above the surface. That means the downward force must be balanced according to Newton's law. So that would be Newton's third law. So we know that if the force of gravity downwards has to be balanced, the balancing force is the normal force. So we can fill that in as it's equal to gravity. It won't always be equal to gravity, but in this case, gravity is straight down. It's perpendicular to the surface. Normal force will be perpendicular to the surface in the other direction. All right, so we've got pretty well all of our forces labeled. We can't do friction because we'd need to calculate it, but we do have all the information now. I hear my phone buzzing here in the background. So the force of friction, let's calculate that first. So the formula for the force of friction is equal to mu Fn. Fn being our normal force, not the net force. Whenever I write net force, I will do Fnet because I find there's too many n's and it gets confusing if you don't include the extra letters. So that just will help you clarify a little bit. Some people use a little n and a capital N. You could do that, but think about the context of the question. In this case, it's normal force. Okay? So the force of friction, we know what this mu is. That's our coefficient, so 0.65. It has no unit, times the normal force of 36.8 newtons. Multiplying those two values together, you will find the force of friction is equal to 23.9 newtons. And you'll notice there's only two sig figs here, so I'm going to round to 2 digits. So 24 newtons. So we can label that in our diagram. Okay, so that's the answer for A. Now we can calculate B. Hopefully that makes sense to you. So we're just kind of working through. Now, I'm pretty sure you've done DC circuits with Andy where you have missing pieces and you kind of have to look at how all the pieces are related in order to figure out current, voltage, and resistance. I've been doing those questions with one of my other classes, and this reminds me of that. Whereas we're working with a diagram, much like you would work with a circuit diagram, and thinking, well, how do all the pieces interact? And in those cases, when I have questions like that, I will often do the math close to the part of the diagram that it relates to, because it helps me keep the numbers in the picture. Okay, so that can be a helpful tool. If you haven't finished that section with Andy, I'll be surprised if you haven't. That can be a helpful strategy for solving some of those questions. Now, B says find the acceleration. Now, if you think back to our last lessons, the only way we can link force and acceleration is if we know the net force. So the formula, according to Newton's second law, his second law says the net force on an object is equal to the mass of the object times the acceleration of the object. So acceleration is going to consider all of the forces. Let's think, does that make sense? If we only consider the force we were pushing with and we ignore friction to figure out the acceleration, what's going to happen? Well, we're going to find our object is moving faster than it really is, because you know from experience that friction will slow things down. So from that perspective, anytime you're finding acceleration, you have to include all of the forces. If an object is falling, I know you know there's air resistance. If air resistance did not exist, turbines would not work very well. Okay, so a wind turbine is all based on how air interacts with objects. So you know that you would have to consider gravity pulling it down, plus the air resistance slowing it down, or air resistance that would be pulling upwards if an object is falling. We've excluded that up to this point, but now we're starting to be able to include those pieces. So anytime you want to find an acceleration, you're always going to be thinking about how do all of the forces on the object interact, and what's the leftover force, or what is the net force on the object. So let's look, where is net force important here? So the vertical forces are balanced. We don't want this accelerating through the table or above the table. That's just some voodoo magic if that occurs. Our acceleration is going to be along the horizontal plane. 45 newtons is the force with which you push. 24 newtons is the force of friction. Now, if I edit this diagram just slightly, just grab my eraser here, I could edit the arrows in order to make it maybe a little more visual for you. So the force of friction is about half the force applied. Now that you can see the arrows and the sizes, we know that the motion acceleration is going to be towards the force applied, because the net force is going to be in the same direction as the applied force. So we just want to, really, net force is going to be the rightward forces subtracted from the leftward forces. So the net force is going to be equal to 45 newtons minus 24 newtons, which leaves us with 21 newtons of net force. Okay, now that we have that, now we can go back to this equation. So we're going to go back up here and we're going to substitute it in. So we know 21 newtons is the net force. That's equal to the mass of the object times the acceleration. Do you know the mass? Yes, that's in our block. So we can say 21 newtons is equal to 3.75 kgs times acceleration. Divide both sides by 3.75. And we have an acceleration is equal to 21 divided by 3.75 gives you 5.6 meters per second squared. I'd say that's a fairly substantial acceleration, it seems. Okay, so that's how you set one of those questions up. You can see it takes a good bit of space to do them. It's not difficult, but you do have to think about how each part interacts. Now, I know you could do one of those questions faster than I talked you through, because I've done all of the kind of explaining behind, but hopefully that helps you better understand. Now let's go on to another example. I told you I had 5 examples. So in this case, we have a 0.2 kg puck pushed along a sheet of ice with a force of 0.24 newtons. If it moves at a constant velocity, find the coefficient of friction. So now we're looking for a new piece. This is a key word. Anytime you see this in a problem, circle it, underline it, something like that. Constant velocity. means F net equals 0. Anytime something's moving at a constant velocity, according to Newton's first law, that means the object is not accelerating, so the net force is 0. So all of the forces are balanced. That should help you as you diagram. So let's do our quick little free body diagram. So we have our puck and 0.200 kgs. All right, we have a force of gravity on it. It's sitting on a surface. Draw the surface if you need to, you don't have to. We have the force of gravity downwards. That's equal to mg, which is equal to 0.2 times 9.81, which is 1. Oops, not 969, it's 96. I sometimes flip numbers. If you ever notice, I know carpentry has caught me a couple times on it, where I've flipped a number. I do my answer keys up, and then I record the lesson after I've done the answer key. So I've really gone through this about 4 times before I actually record it for you. Sometimes I do flip numbers when I'm just reading from my sheet. So if you're ever questioning it, don't hesitate to let me know. That's a problem that I sometimes have. So we have the force of gravity pulling downward. We know there's a force applied, so we'll say it's going, it doesn't really matter which direction you label it in, because it doesn't say which direction, but it's positive, so we'll go in the positive. 240 newtons equals my force applied. We know we have friction, because even though it's ice and it doesn't have a lot of friction, it's going to have a little friction because you know that puck eventually stops. Okay, and then we have another force, the balancing force to the force of gravity. So that's our normal force. And the normal force, in this case, gravity is perpendicular to the surface. The normal force is perpendicular to the surface, so they're both equal to each other, 1.96. Okay. So we have all of our pieces except for the force of friction. So let's stop and think now. What would the force of friction be? We're not given anything to be able to really calculate the force of friction using the formula you had before. But we do know that the net force is equal to 0. So if F net equals 0, then you know that the force applied has to be equal to the force of friction, which must be equal to 0.240 newtons. That makes sense? All of the forces are balanced, so whatever force you have in the rightward direction must be the same in the leftward direction. So 0.240 newtons. Now it's an easy calculation to do. We want the coefficient of friction, and we know the force of friction is equal to coefficient of friction, mu, times the normal force. Now we can go through and plug all of our pieces in. So the force of friction is 0.240. It's equal to mu times the normal force of 1.96. Dividing by 1.96 on both sides, the coefficient of friction is equal to 0.122. And it doesn't have any units, it's just a ratio. So that's our question done. So not a difficult question, but you want to find all of your pieces. That word constant velocity, picking that out and realizing that the forces are all balanced was the key piece to this question. Otherwise, it looked like you didn't have enough information. This one is a great question. It's a little counterintuitive, but I think it'll really help you kind of think about where I'm going to go at the end of this lesson. Actually, just even in the next example. So an 11 kg textbook is held against a vertical wall with a force of 45 newtons. What's the coefficient of friction between the book and the wall? So this is a lot like the last question. So we're looking for the coefficient of friction, so we're going to have to find the force of friction. We're going to need to know the normal force. Okay, so force of friction, is equal to mu Fn. So we need to find both of these pieces. So first of all, let's start with our free body diagram. So here is my vertical wall. And in this question, drawing the wall I think is helpful. And here's our book against the wall. Okay. All right, what forces are on the book? Well, it says the book is held against the wall with a force of 45 newtons. So imagine leaning against a wall and you're pushing into the wall with 45 newtons holding this book into place. That's your applied force. Does the wall push back? Well, you don't go through the wall, so the wall must push back. That is our normal force. So in this case, you'll see normal force. You're not accelerating through the wall. The book's not accelerating towards you, so the forces need to be balanced. And it says it's held against a wall. There's nothing here to tell you acceleration, so that would assume that it's just stationary. Stationary means the forces are balanced as well. So in this case, you'll see the normal force is opposite the applied force because it's at a right angle to the surface. We still need to figure out the force of gravity. Force of gravity is what would pull this book downwards. So if this book moved, it would move downwards, but the book does not move. So that must mean there's a friction force in the other direction that balances out the force of gravity. Okay? Because the book does not slide from your hand. If there was no friction, when you push that book against the wall, it would drop. But because there's friction, the friction opposes gravity, but it has to be equal to the force of gravity. So let's figure out what the force of gravity is. It's equal to m times g. Mass is 1.1 times 9.81. Leaves us with 11 newtons. So if we have 11 newtons downwards, we have 11 newtons upwards. And this is our F net equals 0 scenario, okay? So that's that little piece that lets us solve that. Now that we have that information, we can calculate everything here. We know our force of friction. The force of friction is opposing gravity. It's 11 newtons. It's equal to mu, which is our coefficient. That's what we want to find. And times the normal force. The normal force we found was 45 newtons. Divide both sides by 45. 11 divided by 45 gives us a coefficient of friction of 0.24. Okay. So the key thing here is to notice that normal force is not always equal to gravity. Sometimes that's a mistake people make. They say, well, normal force is always equal to gravity, but it's not. It balances whatever forces are pushing on the surface. Okay, so we're going to find in the next couple questions how that's really going to impact our question. Okay, so the next couple questions we're also going to have where normal force is not equal to gravity. The only time it's equal to gravity is if there's no other vertical forces other than gravity acting on the object and the surface is perpendicular to gravity. So something's sitting on a horizontal surface. All right, let's get a little bit more complex. You guys are good with vectors. Hopefully I'm not jumping in too quick putting these questions in now, but I know you guys know how to deal with vectors, so we're going to move to some vector questions. And use a think and apply question at the very end of this section. So I just have, this is our last two examples, and then you'll be out. All right. And I don't have one of these ones in SAM for practice, and I didn't even put one in the practice worksheet for this section. I'm going to put an angle question in the next worksheet, but I want you to start thinking about angles because starting to think about angles is important. But I also want you to practice simple questions so you don't get overwhelmed at the beginning. All right, so a 215 kg crate is pulled with a force of 2,400 newtons at should be a 15-degree angle upward from horizontal. Imagine you've got a string or a strap attached to something and you're pulling it at a slight angle. Maybe you've got something hooked to the back of a truck with a tow rope. You're often going to have an angle involved. Okay? If the coefficient of friction is 0.19, what's the net force on the crate? And then B, what's the acceleration of the crate? So first of all, you know where I'm going to start. We're going to start with that diagram. So we have our crate, and it's sitting on a surface. It's supposed to be sitting on a surface instead of levitating. There we go. There's our crate. Let's label all the forces that we know. So 215 kgs, we know gravity is going straight down. You might not know the sizes of arrows, and the sizes of arrows aren't necessarily a big deal when you're diagramming if you don't know them, but just using them to help you keep track of directions is helpful. So force of gravity is going to be 215, so mass times gravity, 9.81, which it gives us 2,109 newtons downwards. Don't label normal force yet. Okay, save normal force and label it last. You'll see why in a second. We also know we're pulling on this crate, and obviously I've not drawn my triangle to scale. 15 degrees from upwards, and I'm pulling with a force of 2,400 newtons. Okay? All right. Am I pulling up on the crate? You'll notice this triangle. I'm pulling towards the right and I'm pulling up. If you're pulling upwards on something, are you taking a little bit of the force of gravity, balancing a little bit of that out? Of course you are. Okay, and oftentimes when you move something heavy, instead of just sliding it horizontally, you kind of do the little upwards lift and pull a little because you're reducing friction. Why? Well, the reason that friction is being reduced is we're going to find we have less normal force. First thing though, we need to figure out what are our vector components. I'm going to call this one F applied perpendicular. It's perpendicular to the surface. I'm going to call this one F applied parallel because it's parallel to the surface, parallel, same direction. Let's think about our trig. So here's our angle. This is my opposite side. SOHCAHTOA, S-O-H. So this is going to be sine, right? So we're going back to our trig. So this one uses sine. So if I was to figure it out, the applied force is my 2,400, and I want to know what this is. So we know that the sine of 15 is equal to, you're going to have your opposite, so applied parallel, or perpendicular rather, divided by the force, the total force applied. Rearranging that gives us force applied times the sine of 15. Now you may just recognize some of that from vectors. What I usually will do, and this maybe sounds silly, I often won't write down this whole equation here, but what I will do when I'm doing them is I know from vectors that it's always the resultant length times the sine or cosine of the angle will give me the component vector. So because I know that pattern is true, I just have to decide if it's sine or cosine. And I know it's always going to be that same resultant, sine or cosine, and the angle. So what I usually will just do is I'll just label my diagram, figure out, well, which one's opposite, that goes with sine, which one's adjacent, that goes with cosine. So you can write this piece out, but depending on how much you understand of that. In this case, if you want to memorize this, that would be perfectly fine. Because it's open book, you're not necessarily having to memorize, but you will have to apply it. All right, now that we have this, we can plug in our information. So it's 2,400 times the sine of 15, which gives us a force equal to 621 newtons. So that's our perpendicular force. Now the parallel force is, we got to figure out what that happens to be. Just give me one sec here. Got to get that ringer stopped. All right, now that I got that phone call over with, sorry about that. Let's continue with our solving our problem. So what we had done, it started out, I got to recap for myself. We have our force applied of 2,400 newtons here. A perpendicular force we found goes with the sine ratio. So it's force applied times the sine of the angle. So 2,400 times the sine of 15 gives us 612 newtons in the upward direction. The force that's parallel to the surface, so the force that's pulling directly towards the right, is going to be equal to 2,400. We're just going to change from sine to cos. Cos of 15 degrees, which gives us a force of 2,318 newtons. So we've broken this vector into two. Now, if we're pulling towards the left, we know friction is going to be towards the right. We don't know how big it is. We do know what the coefficient of friction is. But we don't for friction, we need to find our normal force. So the normal force is a balancing upwards force. Now, for this particular question, the upward balancing force is one of those that we're going to really have to stop and think about. So we have normal force upwards, plus we have this perpendicular force that's also upwards. We have two upward forces and one downward force. The normal force will need to be, well, I'm going to write this out a little bit differently. Just give me one sec. Sometimes you start to write something, oh no, this explains better this way. So we know the downward force and the upward force has to balance. So we know the force of gravity needs to be equal to the normal force plus the force applied perpendicular. Because as you're pulling on it, because you're pulling upwards, there's not quite as much force pushing up from the surface because you're alleviating some of that by the direction of your pull. So we can plug in our information here. 2109 has to be equal to our normal force, which we want to find out, plus the force perpendicular, which is 621. Subtract 621 from both sides. I may run out of space based on the way I'm writing things out, but that's all right. Gives us a normal force that is equal to 1,488 newtons. So because you're pulling upwards, the normal force is decreased. Anytime you pull upwards, the normal force is going to be decreased. Let's stop and think for a sec. I'm going to ask this question at the end of the lesson again. What if you're pushing downwards? So you're pushing on the edge of the box as you push. Is normal force going to be larger, smaller, or the same as gravity? There's a question for you to think about as we do our calculations. So normal force, we know is 1,488 newtons, and now we can calculate the force, the force of gravity and the net force. So force of gravity, force of friction. So the force of friction is mu times Fn, which is going to be 0.19 times 1,488, which gives us a force of friction equal to 283 newtons. Now we're ready to finish our calculation for A. So all of that math, and we still haven't solved any of this question yet in terms of what we were actually asked for. So for A, net force. The upward force and the downward force, they're balanced. So we're just looking at what's the difference between left and right. So the net force is going to be equal to, well, we know the parallel force. We have a rightward force of 2,318 newtons. We have a leftward force of friction minus 283 newtons, gives us a net force that is equal to 2,035 newtons right. Okay, so when I'm finding normal force, I just stick horizontal. Get my words straight. If I'm doing normal force, I stick with all vertical forces. I only look at vertical forces when I'm dealing with that. Then when I'm finding my net force, I deal with my just horizontal forces because that's the direction of motion. So you're kind of isolating things, just kind of like when we did projectiles. We isolate vertical and horizontal. We don't work with them together. If we could work with them together, we wouldn't have to break things into components. All right, B, what's the acceleration of the crate? The acceleration of the crate, well, we know F net is equal to mass times acceleration. So we have a net force of 2,035 newtons. That's equal to our mass of 215 times our acceleration, divide by 215. And we get acceleration is equal to 9.5 meters per second squared. And we can just remember our units from before. So force is going to be in newtons, mass in kg, and meters per second squared for acceleration. That question may have felt a little overwhelming. If it did feel a little overwhelming, you're a very normal student. We're going to do another one. Okay, so when we start to throw in some angles, people tend to find, oh, it's a little bit complex. But if you remember, break things apart, look just horizontal and just vertical. Finding a strategy that helps you organize your information is going to be helpful. I like using the picture. If you have another strategy that you use for organizing the information, please share it with us, share it with your classmates. That's one of the things I miss when I don't see you in class, is sometimes just from even circulating around a classroom, I observe different methods of tracking information, which gives me strategies for students that may struggle. So if you're wondering, or if you're not sure, if you have a good strategy, please don't hesitate to reach out and let me know. So our last example is going to be similar to the last one. It won't take us too long to calculate. I think this one might be a little easier to calculate. All right. A 150 kg crate is pulled at a 45-degree angle. So we're going to assume it's pulled upwards. We can do a pulling downwards, but that does not usually make a whole lot of sense unless it's unless we're moving something that's taller than we are, with a force of 750 newtons. What coefficient of friction would be needed to make the crate accelerate at a velocity of 2.5 meters per second squared? So if I want to find coefficient of friction, I'm going to need to figure out what is the force of friction. First thing, before we get into figuring out a whole lot of the problem, let's start with what we know. Label the easy pieces, label the information that we can figure out. So we have our crate on our surface. It's 150 kg. I've modified this question 3 times, I think, while I was doing my key up, because I made it up without doing an answer key. I did my answer key, found the question didn't work. So hopefully I've got everything rearranged correctly this time. There's my applied force, and it's equal to 750 newtons. We can break it into 2 components, and we'll calculate our components in a minute. We also know we have a force of gravity. We must have a normal force. We don't know what it is. And we know for sure, because the question talks about friction, there will be a friction force. Okay, so we have all the forces labeled. We don't necessarily have their sizes in. So for the force of gravity, I'd like to start with the force of gravity first because it's an easy one. So we're calculating a weight. So 150 kgs times 9.81. 150 times 9.81 leaves us with a force due to gravity of 1,472 newtons. Now you know you can't just put the force of gravity in for normal force because we're pulling upwards too. Okay, so because we're pulling upwards, we're going to have to figure out, well, how much force do we really need to balance this? If we need to calculate. All right, so, but we can break this into its components. So we have 45 degrees. Nice thing about 45 degrees, anytime you have 45 degrees, the horizontal and vertical components will be identical. So once you've calculated one, you know the other. So we know vertical, this is the opposite side, so it's the one that uses sine. So it's going to be 750 times the sine of our angle. So 750 times the sine of 45 is 621 newtons. All right, so that's the force. I'm going to say force applied perpendicular. Force applied parallel is going to be exactly the same because it's 45 degrees. You can test it if you want using cosine, but it's going to be the same. Oops, I copied down the wrong number here. Just give me one sec. I have 2 slides on my handout that I'm working from, and I just realized I copied down the wrong force. I read the wrong question. 750 times the sine of 45 gives us 530 newtons. There we go. Now that we have that, it'll help us out. All right, what's the normal force? Well, we need to find your normal force, and we know that the normal force and the force of gravity plus this applied perpendicular force have to balance out. So the force of gravity is equal to all the upwards forces, which is normal force plus the force applied perpendicular. So the force of gravity is 1,472. It's equal to my normal force plus force applied perpendicular, which is 530. Subtract 530 from both sides. And we find the force normal is equal to 942 newtons. Okay, not done yet. I drew a box around that. I guess it's just a habit when I finish off the calculation. 942 newtons. That's one piece to finding what friction is. But the issue is that I don't know the coefficient of friction. So what other information could I use to find out friction? Well, if we look back in the question, it did say there's an acceleration. So that means there's a net force. So what is the net force? Well, the net force is equal to mass times acceleration. So I go back and we'll calculate it. 150 times 2.5 gives us a net force that is equal to 375 newtons. Okay, so now I can find out what the force of gravity is. I know that there's a force pulling forwards that's 530 newtons. The opposite direction is the force of friction, which we don't know, but we know if we subtract those two, we're left with a net force of 375. So our net force is going to be equal to the force applied, and it's the parallel force applied, the one that's in the same direction as friction, same direction as the surface, same direction as the motion, minus the force of friction. Plugging in our values, we end up with 375 is equal to 530 minus the force of friction. If you rearrange that, you will find the force of friction is equal to 155 newtons. Now our question's easy to solve. So we've got all of these pieces figured out. The final solution we'll put right here. Force of friction is equal to mu Fn. 155 is equal to the coefficient of friction times the normal force of 942. Divide by 942 on both sides. And our coefficient of friction is equal to 0.19. That's the final answer. So a lot of little pieces come into play in order to figure out one of these problems. Question 4 and 5 are the more complex ones. So your worksheet's going to be simpler than these to start out, but you do need to think about them. And these questions should help you with what we do in our next lesson. Now, just a couple things before we finish off to remember about normal force. Normal force is often, but not equal to the force, often equal to weight. Let me read that properly. It's often, but not always equal to weight, okay, or the force of gravity. So if there's no other vertical forces, it will be equal to gravity, assuming that you're sitting on a horizontal surface. It will always be perpendicular to the surface. That will never change. And it's always going to balance out the forces applied to the surface. So it's always that balancing force. Sometimes you have to include gravity plus another upwards force. Sometimes you might actually have to include a downward force. To find the normal force, all the forces Diagram all the forces that are perpendicular to the surface using your vectors if you need to, and then balance those forces so that your net force equals 0. So that will help you out when you find your normal force. Now, for most of your worksheet questions, you will be able to use your normal force equal to gravity. So that will start out easy. And for your questions that you have in SAM, that will be true for most of your questions. I won't give you normal force with an angle or anything like that until it's something you hand in so we can see process, although I'm trying to get caught up on marking. So I'm not rushing to give you something that you have to hand in for me to grade. Finally, I want to finish with a think and apply question. If there's friction between the 100 kg block of ice on the surface, which scenario will require more force to move? So in the first one, we're pulling upwards at 25 degrees. In the second question, we're pushing downwards at 25 degrees. Now, if it's exactly the same surface, we know the coefficient of friction is the same. If the block is the same weight, we know the force of gravity is identical. The only thing that's going to change this is how does my push impact the normal force? So let's look at just quickly, we're going to just diagram and we're not going to do any math, we're just going to think and apply. So we have gravity pulling downwards. We know that a normal force balances upwards. But there is also my force applied that's upwards, that perpendicular upward force. Will my normal force be bigger than gravity or smaller than gravity? My normal force will be less. Because as I'm pulling, I am actually creating a balance force to the force of gravity. I'm not balancing all of it, but some of it. So my normal force will be less in the first scenario. Friction depends on normal force. So if the normal force decreases, the friction should decrease. There's less contact force between the two surfaces. What about in this case? Well, in this case, you're pushing downwards. So we have gravity pushing downwards. You also have an applied force downwards. One of your vector components is going to be downwards. Normal force is upward. In this case, the normal force has to balance both gravity and the applied force. The applied force isn't helping relieve normal force, but in fact, it's increasing it. So in this case, we're going to have more normal force, more, M-O-R-E, more normal force. And because there's more normal force, we're going to have more friction. If we have more friction, which one's going to be easier to move? The first one, because you're actually, by lifting upwards a little bit, you're resulting in less friction. So if you want to make yourself less work, think about the angles at which you push or pull objects. And that's actually something that can come into play when you're doing some rigging questions or you're doing lifts. I remember it's been a couple years since I spent an afternoon being a dummy in the Witten shop. We traded places with the class. I played the dummy for the day. And they were just simulating rescues. And I think they thought I was going to be a little lighter than I was because some of them did some good huffing and puffing by the time they were finished. I think I might have even surprised Andy. But it was interesting because we had just finished a section with forces and it was just before going out on OJT. So it was really interesting to look at how people, what directions they pulled. So whether they were pulling out at an angle or whether they were pulling almost perfectly vertical. And how that actually helped them exert less force in order to lift my slightly heavier body than they realized. We're going to deal with a couple questions like that next week, just before we finish off our forces section. We're just about done through forces. We've covered almost all the scenarios, but that's going to be kind of our practical application is how can I use force to help me in a situation where I'm doing a rescue? In particular, if you've got a heavier partner than you thought, and maybe you don't have as much strength,
or maybe you don't have as much body weight in order to be able to move them. So there are some really good applications to think about, and vectors can come into play. But this is just simply if you have to load something onto a vehicle, instead of pushing downwards to move it, you want to try push. I would recommend you want to try push either perfectly face onto it so you don't have that vector. So that way normal force is equal to gravity, or in a best case scenario, find a way to tie around and pull it. And pulling is typically easier than pushing just because you have less friction force. It may not be a lot, but any reduction in work is better than no reduction in work. So hopefully that gives you a good understanding of how forces work, gives you some good background, and lets you go through and work at your quiz.